So can you guys see my screen now?
Yes, sir.
Right. So last meeting, we have just finished discussing this voltage to current converter. So of course, it has its own opposite, wherein we have the current to voltage converter or amplifier. Okay. So this is the same concept with the voltage to current converter. It's just that in here, our source now is the current, and then our output now will be our voltage source. Okay, so this one is a lot easier than the first one because this one is very straightforward. So as you can see from Ohm's law, that voltage is equal to current times resistance. And in fact, an ordinary resistor can be used as a current to voltage converter. Okay, so you don't actually need an amplifier, okay, an op amp, just to have a current to voltage converter. Okay, you can just have a simple resistor. So yeah, if you connect a resistor to current source, the resistor will generate a voltage that is equal to the current multiplied by the gain, okay, like the resistance. But since we are under the op amps, so in here we will apply current to voltage amplifier with the use of op amp. Okay, so using this circuit like a voltage follower, but instead of instead of having an infinite uh, resistance here, we do have a value of RF here, or the feedback resistance. Okay, and then how do we solve for the voltage output? So we have this formula, which is negative uh, input current times your resistance or feedback resistance. And as you can see, our voltage output will become negative due to the polarity of our feedback resistance. Okay, so that is why we have here the negative. And yeah, this is the much more formal uh, circuit of the current to voltage converter. So we do have here a current source, okay, which can also be found on the LT spice. And then we have here the V out, and then we have here the uh, load resistor. Okay, so let's create a simple current to voltage converter using an LT spice. Okay, so new schematic. So again, of course, we're going to use OP07, okay, the precision operational amplifier. Okay. Then of course we need rail voltages. This will be our power supply, our peak to peak power supply. So we need voltage, of course. So let's see, 12 volts. So, and we have here a resistor, which is our feedback or RF feedback resistor. And then let's say we have here 1K for now. And then the new thing in here is, of course, the current source. So just go to the components and then you will see this current. Okay, so just click that one and then just click OK. And then, of course, be mindful with its polarity. So it should be going up. Okay, this one is an indicator that this one is a positive and then negative polarity. So positive and then negative. So we have a positive current and then it will be negated once it already passed through our feedback resistance. Okay, so I'll just put a label here, label for the V out. There you go. And say we have RL here, which is also 1K. And then a ground, of course. Ground and then ground. Okay, let's see. And then this one is also grounded, and then just a connection here, which is also grounded. So there you go. So from here, we can now put a value for our current source. So just right click and then let's say 5 milliamps. Oh, so 5 amp. Okay. So we are expecting a voltage output of, so I is equal to V divided by R. So sorry, V times I times R, since this one now is a current to voltage converter. So we are now expecting a voltage. So V is equal to I times R. So I is 5 milliamps times 1000 is equal to, so you can use your calculator. So we'll get 5 volts. Am I correct? Or no? 5 milliamps times 1 kilo. Am I correct? Anyone who has a calculator on his side?
Yes, sir. 5 volt.
5 volts. Okay. Okay, so let's see whether this one is really getting a 5 volts or no. So let's run this in 50 milliseconds. So our input has, oops, our input has a 5 milliamps, okay, DC. And then once it passes through this feedback resistance, we should get 5 volts. Okay, so there you go. We have 5 volts for the V out. Okay, well, not exactly 5 volts, but at least super close, negative 4.99999. Okay, and then take note this one is negative since we have the polarity of positive negative feedback resistance. Okay, so introducing your laboratory 12, okay, which is current to voltage converter plus and then current to voltage converter plus and minus. So for the 12A, this one is super simple. Design a current to voltage converter with positive voltage output only. Okay. So why positive voltage output only? Because if you will make this one a sine wave, okay, let's say 5 milliamps and then at 60 hertz. Okay. So we will have an input of an AC, and then of course we will also have an output of AC at the same time. And as you can see, this one is accepting a positive and negative current voltage at the same time. Okay, so this one is completely out of phase. So when we say out of phase, this one is 180 degrees opposite of the original phase. So if we have positive input, we have negative output. If we have negative input, we have positive output. Okay, so what I want you guys to do is add a component wherein this will only accept a positive output, or this will give us only a positive output. Okay, so I should not see this negative waveform. So I should only see positive waveforms when it comes to V out. All right. So that's it for the 12A. Okay. And then for the 12B, okay. Actually, I have already answered the 12B. Anyway, since this one's just like a bonus already. So 12B, I should see a current to voltage converter circuit, and then of course having an output or voltage output of positive and negative. Okay. So I've added a hint here on how you will make this one, or how will you filter out the negative waveform. So you can use a Zener diode or just a diode to get the preferred voltage output. All right. So this one is super easy. And then the same for the last one, just like the reflection or conclusion, and then the benefits of this kind of circuit in our industry. Right. So any questions so far regarding with your uh, laboratory 12?
None, sir.
All right. So we have already answered 12B. Your only problem now is 12A and then 12C. All right. So this one is super easy anyway. The next one is instrumentation amplifier. Okay. So what is this instrumentation amplifier? So it is an amplifier that allows an engineer to adjust the gain of an amplifier circuit without having to change more than one resistor value. Okay. So compare this to a differential amplifier, because this one actually came from a differential amplifier with additional two buffer or voltage follower. Okay. So which we covered previously, which requires adjustment of multiple resistor values. So as you can see in differential amplifier, so there's a lot of resistors that you need to tweak, you need to change just for you to get the preferred voltage output. But with the use of instrumentation amplifier, yes, we do have a more complicated circuit than the differential amplifier, but you only need to change one resistor. Okay, let's say initially you have an output of 5 volts, but you want to make it more higher or make it more lower, then all you need to do is change the value of your R gain. Okay, so the rest are actually the same value. So all of those are the same values of resistors, other than or except the R gain. Okay, because this is like your controller. Okay, this is where you control the voltage output that is being provided with this instrumentation amplifier. And one reason why this they call this one instrumentation amplifier is because they use this kind of circuit to test a device or a circuit or anything actually. So this one is like a testing circuit. Okay, so as I have said a while ago, so considered all the resistors to be equal value except for the arcane, which is this one, the middle resistor. And then we do have this formula. So again, this one is kind of similar with the differential amplifier. So we have the V2 minus V1 times 1 plus 2 times R divided by R gain. So whatever is the computation on the V2 minus V1 will be amplified with this kind of formula, 1 plus 2R divided by R gain. R gain. So this one has a derivation. Okay, so there's a lot of articles and there's a lot of call this one a website that uh, this formula came from or derived from. Okay, so this one has a long process when it comes to simplifying this kind of circuit. So initially they only have this differential amplifier, so it's longer than that, and then they've added this one, and then they simplified it again, and then they've added another one, which became a totally instrumentation amplifier, wherein they've come up with a simpler formula, or a more simplified formula, which is now this one. Okay, so for V2 minus V1, this is just simply the inputs on our buffer or on our voltage follower. So just take note on the signs. So we have here, let's say this one is grounded or going to the resistors. So the same with this one negative. So inverted input and then inverted input. And then our inputs will be coming from the positive voltage follower. So positive here and then positive also here. And then lastly, we have here the look-alike circuit of a differential amplifier. Okay, so that is why uh, this one is a little bit similar when it comes to differential amplifier. All right. So what are the advantages of the instrumentation amplifier? So the first one here is it is possessing extremely high input impedances on the V1 and V2 inputs. Why? Because they connect straight into the non-inverting inputs of the respective op-amps. And it's adjustable gain that can be set by a single resistor only. So before we have to tweak many resistors, but in instrumentation amplifier, just only one, which is the R gain. Okay. Second, it eliminates the need for input impedance matching. Okay. So before we were worried, will this be enough or will this be good to match the, let's say, voltage to current delivery or current to voltage delivery. So in here, you don't need to mind that one. Okay, so no matter how high is the impedance on your input, so it's okay to your output. Okay, so doesn't have that much effect on our output, and thus make the amplifier particularly suitable for use in measurement and test equipment. So as I have mentioned a while ago, this one is mostly used to test some equipments or devices or a certain circuit. Okay, all right. So using this circuit, let's create this one on the LT Spice. So let me just erase this one and maximize this one. All right. So of course, we need an op amp, which is still the OP07. There you go. And then this one, of course, has a real voltage. Positive, negative. And then those two are, of course, grounded. And then this one, let's say, so I'll just I'll put it to the, I'll put it to a large value, okay, not maximum, because we cannot say that this is the maximum value. But I'll uh, put here 100 volts. So this is already an exaggeration. But anyway, just to be safe, okay, because this is our peak-to-peak limitation of our output waveform. Okay, and then we have here the two resistors, 2, 4, 6, 7. So 2, 4, 6, and then 7. All right, so this one is like our feedback resistance. Same with this one. This one is grounded. Connected. All right. So this one is also connected here and here. This one right here and here, and here, here. There you go. Correct. And then, of course, to another op amp here, which is still the OP07. OP07. Okay. So one here and then another one right here. Oops. Okay, so let me just copy this one. And this one is connected right here. And as you can see right here, we have positive on the lower portion of our op amp, but in here we have the negative side. Okay, so for you to interchange those two, so highlight this one first, and then the next thing that you want to do here is rotate, Control R. Okay, so rotate it on that side and then mirror it. Okay, so I forgot the shortcut key for the mirror, but I'll just do it here manually. Okay, so this is the mirror, and then this is the rotate. So I'll click the mirror one. So there you go. So from there, we now have the negative below. Okay. But of course, be wary also when it comes to its VCC and VAE or your real voltages. So your negative is now on the upper side, and then the positive now is on the lower side. All right. So of course, we need to have a voltage supply for this one. And this one is connected here also, correct? And then we have here the 2 voltage input. So positive to positive. And then of course, they are also grounded. And then 4 more voltage source. So negative right here, and then positive right here. And then for the other side, this one is positive, and then this one is negative. Okay, there we go. There we go. Then this one is grounded. This one is, oops, grounded, grounded, and then grounded. So there you go. We have a total of 2, 4, 6 rail voltages. Okay, and then two another voltage inputs for our op amps. And then this one is connected here, and then this one is also connected here. All right, so we're now done, I guess. Not yet. So this one is connected right here. And grounded. So did I miss something? This one is not connected. Right. So we're good to go. So from here, says here that all of the resistors are equal in value except the R gain. Okay. So I'll just put here 1K, 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 1K. Okay. And then say for now this one is also 1K. Okay. So this is the only resistor that we can change as we control, or let's say call this one, mm, make the voltage output higher or lower. Okay. And the same with the rail voltages of your voltage follower. So we also have here 100 volts, 100 volts, 100 volts, and then 100 volts. Okay. And then let's say your V sub 2 is equal to 5 volts, and then your V sub 3 is equal to 2 volts. So using the formula, I would like you guys to get your calculator, and then yeah, uh, apply this formula on our LT spice values. So oops, we have V2, which is equal to 5 volts, and then V1, which is equal to 2 volts. So I will also use my calculator. So 5 minus 2, and then 1 plus, so your 2 here is still 2, and then your R here is the equal value of resistors, which is 1K. Okay. And then for the R gain, so what we have set in here is also 1K. So just put there also 1K. All right, so what did you guys get?
9, sir.
So we have here, yeah, the same with me, we have the same answer, which is 9 volts. All right, so let's see whether this one is really correct or no. So we run this one for 50 milliseconds. Okay, so let me just include a label, V out, for this side. All right, so there you go. So we have 9 volts. Okay, so just double click this one, then you will see this 9 volts. Okay, so if you're going to do this one step by step, so here you can see that this one became negative 1 volt now, and then this one became still 2 volts rather, and then this one is still 5 volts, and then this one will become 8 volts. And then as you can see right here, it will pass through this resistor, R5 and then R3. So your 2 volts will become negative 1 volt. So why is that? Because this one is like working a voltage divider on this side only. But on this part wherein your V sub 4 will pass through R6 and then R4, it's not the same as like a voltage divider. Why? Because it's already getting a feedback from our voltage output, or R1 or R2. And then as you may recall, amplifiers or op amps, operational amplifiers, tends to equal the two inputs. So mostly the inputs here in negative is the same with this positive input. So as you can see, if we're going to click this one, so 4 volts, and then for the positive, it's also 4 volts. So that is why this 1 volt is not the same with this one anymore. Okay, so supposedly we're expecting 2.5, right? But it's not the case anymore. So as you can see, it's now 8 volts. Okay, so due to the feedback resistance of this amplifier. All right, so this one is correct, which is 9 volts. Okay, so let's say we want to lessen the voltage output. Of course, all you need to do is change this one, change the value of your R gain. So let's say 500 ohms. So let's see what will happen to your output. Okay, what did I say? Lessen? Sorry, what I mean is we want to have a higher voltage output. Of course, the lower the resistance, the higher the voltage output. So in here, we've just lessened the R gain. Okay, and then we've now got a total of 15 volts as your V out. So if you want to have a lower voltage output, then just make this 100, let's say 2K. Okay, and then you will get 6 volts. So before this one is 1K, we've got 9 volts, but right now we've just changed this one into 2K, then we've now got 6 volts. So as you can see, you only need to tweak, or you only need to change one value of resistors instead of changing 3 or 4 or more. All right, so let's introduce your laboratory number 9. Just remember, okay, so okay, so let me change this one. Okay, so your 13A, so it says here, design an instrumentation amplifier with a voltage output of 9 volts. But we have accidentally, okay, get a result of 9 volts in here. So instead of 9 volts, I would like you guys to uh, have an output of 20 volts. Okay, a voltage output of 20 volts. Okay, so assuming that you have 1 kilo ohms on all resistors, including the R gain. Okay, so I would like you guys to come up with a result of 20 volts. Okay, so as usual, of course, you're going to use the precision operational amplifier. And then for the 13B, okay, so design an instrumentation amplifier with a voltage output of 5 volts, assuming that you have 1 kilo ohms on all resistors, excluding the R gain. Okay, so in here, the one that you're going to tweak or to change here is the R gain. So for the 13A, the one that you need to change is the voltage inputs, your V1 and V2. But in here, V1 and V2 is already given. So for V1, it's 10 volts, and then V2 is 15 volts. Of course, they are sinusoidal wave or AC input. So the same, use the proper amplifier on this, which is designed to work as a precision operational amplifier. So as usual, you're going to take a screenshot of your schematic and then the graph of the current input and then the voltage output. By current input, voltage input, and the voltage output. There you go. And then the last one, so saying this is like a reflection or conclusion. So from those circuits or problems that you have accomplished, what are your thoughts about instrumentation amplifier? And then what are the benefits of it in our circuit industry? So give a scenario on where we use such circuit. All right. So any clarification so far regarding with your laboratory number 13? All right. So none coming from Mr. Eda. How about the others? Do you guys have a
None,
question or
sir.
None,
clarification?
sir.
All right. So if you guys do not have a question anymore, then that's it for the laboratory number 12 and then laboratory number 13. Okay. So yeah, you guys may now go, and then see you next meeting.
Thank you, sir.
Thank you too,
Thank
and
you,
thank you.
sir.
Thank you,
Bye.
sir.
Bye. All right, so can you guys see my screen now?
Yes, sir.
All right, so last meeting we were able to finish the instrumentation amplifier. So now we're going to talk about integrator and differentiator amplifier, right? But before integrator and differentiator amplifier, let's talk about capacitance first. So maybe most of you know what is the functionality of capacitance already, but to those who doesn't know, so here's the concept of a capacitor or capacitance. So capacitance can be defined as the measure of a capacitor's opposition to changes in voltage. So the greater the capacitance, the more the opposition. Okay. So let me just give you a quick scenario for this opposition. So what do you mean by opposition? So for example, your input is a sine wave. Okay? We have this sine wave. Actually, this one is a half wave sine wave. Okay. So as our input goes up, okay, it also goes down, right? And as you can see in here, it reaches the zero voltage. But if we have a capacitor in our circuit, okay, it won't reach the zero voltage. Instead, it will give you a voltage, okay, or a current. So it opposes the zero voltage. Instead, it gives you a voltage, right? So this is like a battery that it will give you a supply once there's now out of voltage in your circuit. Okay, so it's like a backup battery in our circuit. So capacitors oppose voltage change by creating current in the circuit. So that is they either charge or discharge in response to a change in the applied voltage. So the more capacitance a capacitor has, the greater its charge or discharge current will be for any given rate of voltage change across it. So the equation for this is quite simple. Okay, so we have this equation right here. For you to be able to get the current, it's equal to the capacitance times the derivation of your voltage divided by the derivation of time. So time here matters because how long will it, let's say, rise, and then how long will it fall? Okay, just like this one. How long will it rise? Like for example, let's just assume that this one will run for 5 milliseconds. So at half of it, it reached the peak voltage at 2.5 milliseconds, and then at 2.6 milliseconds up to 5 milliseconds, that is the falling part of your input. Okay, so that is why we have here the time divided by the voltage. Anyway, it's just the concept. So imagine if you're confused about capacitor, imagine this one as your backup battery when there is a loss of current or voltage in your circuit. All right, so let's now move on to the integrator amplifier. So this one is actually super simple. Okay, so as you can see, this is the circuit of the integrator amplifier. So if you're going to take a look at this one is actually an inverting amplifier. Very look alike. It's just that instead of having a resistor here, we have a capacitance. Okay, so an integrator, or by replacing the feedback resistance in the call this one inverting amplifier with the capacitor, we now have an RC network. So we have the R in and then the capacitance network connected across the operational amplifier's feedback path, producing another type of operational amplifier circuit, commonly called an op-amp integrator. So if you change this one from feedback resistors to capacitance, then you are now creating, or you are now making the op-amp integrator. Okay, so simple as that. So op-amp integrator is an operational amplifier circuit that performs the mathematical operation of integration. That's why it's called integrator. So that is, we can cause the output to respond to changes in the input voltage over time as the op-amp integrator produces an output voltage which is proportional to the integral of the input voltage. So in other words, the magnitude of the output signal is determined by the length of time a voltage is present at its input. Okay, so in here, the length of time of a voltage is very important. Why? Because we're using a capacitor. And also, the charging time and then the discharging time of your capacitor is, of course, depending on its value. Okay, the higher the capacitance, the more that it will oppose your output. The lesser the capacitance, the more that it will not do anything, or it will not change anything to your input and output. Right. So here's a continuation for the integrator amplifier. So basically this one is just an explanation on why we're having uh, like a shipment from the input to the output voltage. Okay, like what is the difference between the output and how did it become like this to the output? Okay, so I will leave the reading part with you guys, but here it's just explaining. Explaining that uh, the time that it will go up and then go down will be affected due to the capacitance. Okay, so yeah, basically here's the formula on how to get the voltage output if you want to do it manually. If ever, let's say you have the voltage input, you have the R in, the value of the capacitance, the value of the uh, what else? The frequency, and so on and so forth. Okay, but we can also use this one. Okay, this is the simplified formula of this one. So instead of using a derivation, so you can just use this one. Okay, so W here stands for 2 pi f, and the output voltage V out is a constant 1 over RC times the integral of the input voltage V in with respect to time. Right? So that's how you calculate the V out if you're going to do it manually. So here are some applications and advantages of an integrator. So the main use of an integrator with this circuit is with the analog computers or analog digital converters and a wave shaping circuits. So we cannot, or I cannot show the examples of analog computers to you since we don't have a system wherein we're going to be needing an integrator circuit and then uh, show the output on the computer. So the only thing that we can do right now using our LT Spice is the wave shaping circuits. So with the use of integrator, we can actually control the shape, the output or the outputs of your circuit, okay, or your waveform. So a common wave shaping use is a charge amplifier, and they are usually constructed using an operational amplifier, though they can use high gain discrete transistor configurations. So any op amps can actually do it, but of course there is a cons wherein you're going to get a very high gain, like an infinite gain. Okay. Another one here is an integrator circuit produces a steadily changing output voltage for a constant input voltage. Like if you have a changing output voltage, so you can use the integrator to stabilize your output. Okay. So you can see that integrator is also a stabilizer. All right, so let me show to you guys this one. Capacitance and then resistance. All right, so I will put this one aside for now. So this is the circuit. Okay, this is the circuit of the integrator. So we have a 1 volt input at 1 volt input at a 60 hertz, and then we have here uh, input resistance or Rin, which is equal to 1K. And then we have here the capacitance, which is equal to 0.01 micro farad. And then we have here the real voltages, so 100 volts peak to peak, and then 100 volts for the negative. And this one is running for 50 milliseconds. Okay, so I didn't show to you guys the step by step on how to do this one, since this one is very similar with the inverting amplifier. Just change this one into a capacitance. All right. So for now, let's take a look. What is the output of this one? Why is there so many? Oops. All right. So we have an input of course, 1 volt peak to peak, positive and negative. And then if you're going to check here the out, we have here uh, negative 100 volts to positive 100 volts. So as you can see, this is already the maximum limit of our real voltage or power supply. So as you can see, it's not usable. So this one is similar with the op amp, or just an op amp or an open circuit op amp, due to a very low capacitance. Okay, so if you want to control your voltage, then you have to put here a high capacitance. So from 0.01, let's make it to 10 micro farad. So as you can see here, just by changing the capacitance, uh, of course, this one now requires a higher charging time and then discharging time. So as you can see, we have positive 1 volts for the input, and then for the output, we have almost half, like 0.5 volts, and then going back to like at least 0, I guess. So it says here negative 18 actually, but this one is almost close to 0. Okay, so maybe you guys are wondering, sorry, why is it only giving us an output of negative only? That is because this one is connected to the inverting amplifier, and as usual, this one has a negative formula on it. Okay, so that is why we have only negative uh, outputs. All right. So for you to be able to control this kind of output, let's say you want to have a positive and negative output. Okay. We have here a circuit called, where is that one? Okay. You have your circuit called the AC op-amp integrator with DC control. So all we need to do is just add this one, okay, this resistance on the top of the capacitance. So let me just connect this one again. And then let me just bring back this one, the value of capacitor to 0.01. Right, so this is the original, wherein this value 0.01 micro, it's like the minimum capacitance that we can put in here. It's like we're not changing the value of your input going back to the, or going to the output. Okay, so let's see. So we have here an input of 1 volt, and we have here an output of negative 10 volts. So how did we get this negative 10 volts peak to peak? So as usual, if you have positive inputs, you have negative outputs, since this one is like uh, inverting amplifier. Okay, so as you can see right here, we only have RF and then Rin. And then as you can see, this one is the minimum value of capacitance. So if ever that you change this one, then there is a change output on your waveform already. So we will not change this capacitance value. So the only thing that we will change is the feedback resistance and then the Rin. So going back to the formula, So to get the gain, we have this negative R2 divided by R1. So as you can see, we have 10K here and then 1K. So 10K divided by 1K is 10. So we have a gain of 10. So multiply that 1 to our input. So that is why we have uh, 10 volts or negative 10 volts or positive 10 volts peak to peak. Okay. So that's our multiplier. So if you're going to put here 5K, then we have a gain of 5. So it's like our multiplier of our voltage output. Okay, so you will get here a peak to peak 5 volts to negative 5 volts. Okay, so just by adding this resistance here, which is called the AC op-amp integrator, okay, so we can now have the perfect integrator circuit, okay, or like a more controlled output of your circuit or of your input. All right, and one more thing here is no more. Okay, so I thought I put here the summary when it comes to the integrator. Anyway, so let me introduce to you your laboratory. So for your laboratory, since we can only show the output shape or the shape waveform or the changes of shape output. So that's the only thing that I will ask you to do. Okay, so for integrator, design an integrator amplifier with a voltage output shape of square wave. Okay, so you can use any kind of integrator. So we have one type here, which is the AC op-amp integrator. There are lots more that is related to integrator. So we even have ramp integrator. That is another concept. So yeah, I would like you guys to find a circuit, or you can use this one instead. And just by changing the sign into pulse. So if you want to get a square wave or a triangular wave, I would like you guys to make an experiment on this one. So uh, put here, let's say 100, 200, 0, 0, and then let's say 10. So I would like you guys, it's your experiment, okay? So I would like you guys to find a value for the pulse and then come up with a result of square wave. Just like what I'm asking for your integrator amplifier. Okay. And then same with the differentiator amplifier. So they are basically the same concept. It's just that a different arrangement of components. Okay. So in here, I'm asking you guys to come up with a circuit wherein we have an output of triangular wave, okay, or triangle wave. So I haven't saved this one yet. I was actually looking for your uh, laboratory for this one, but I cannot find anything since they are too simple. And there's only one thing that I have to think of, which is changing of waveform. So that is why just those waveforms. All right. So do you guys have any question so far regarding with integrator? So of course we'll discuss differentiator later on. All right. So an answer coming from Mr. Eda. So let me just repeat. This one is not a usable circuit since this one's like an open loop when it comes to have a gain. Okay, it's like 1,000 millions of gains. So instead, we have this kind of integrator, call it the AC op-amp integrator, for us to have more control to your outputs. Right? All right, next. So we have here the differentiator. So if you're going to take a look at this one, the only difference is the uh, components, wherein the first one here is the capacitance and then the second one is the resistance. So in integrator, resistance first, and then for the differentiator, capacitance first. Okay. So differentiator amplifier produces an output signal, which is the mathematical operation of differentiation. So that is why they call this one a differentiator. So that is, it produces a voltage output, which is proportional to the input voltage's rate of change and the current flowing through the input capacitor. So in ideal cases, a differentiator reverses the effects of an integrator on a waveform. Okay. So basically, this one is like the opposite of the differentiator, okay, and then vice versa. Okay, they are completely opposite with each other. So having that in mind, of course, this one also has also has a capability to change a waveform. So if you have an input signal of square, you're going to get, let's say, spike. If you have triangular as your input, you're going to get rectangular as your output. If you have sine wave, you will get cosine. So the one that I will show to you guys is sine wave, because the one that I'm asking you to do is the square wave and then the triangular wave. Okay. So we have here the circuit of differentiator. All right. So as you can see, I didn't change anything. It's just that my inputs now are different. So I have now a 10-volt input and then running at 100 not kilohertz, 100 frequency. Okay, and then a capacitance of 0.1 microfarad and then 10 kilo ohms for my uh, R1. Okay, and then one more thing here is, so let me just remove this one. So this one will run for 100 milliseconds. So we have the input peak to peak 10 volts, and then if you're going to click the output, you will get this one. Okay, so it's like a fast-paced output. So as you can see right here, we have a very fast-paced output, -4 to -1, -2 to 1, and so on and so forth. So to fix this one, go to the simulation. Oops. Edit the simulation, and then you have to set here the time to start saving data into 50 milliseconds. So at exactly 50 milliseconds, it will save the data now to our capacitance. Okay? So not at exactly 0 milliseconds. So that to avoid that, a fast-paced changing or charging and the discharging time of our capacitance. Okay, since our capacitance is super small, so this one will quickly charge and then discharge its uh, voltage or current. Okay, so to solve that one, it will only start in saving the data at exactly 50 milliseconds. So right here, okay. So it will save every 50 milliseconds to be exact. All right, there you go. So as you can see, we now have like a smoother output. So as I have mentioned in here, so if we have an input of sine wave, you'll get a cosine sine. Okay. So how did I get this cosine sine? So this one actually has a computation, but I haven't uh, showed it anymore. But you can find it on the internet. Okay. So you can find the formula, and then it will only require you the capacitance value, the resistance value, the voltage input, and then the this one, the 1/2 pi for the frequency, because frequency is not given. Okay, so let's now go back to the spice. So as you can see right here, we have a sine wave of an input and then a cosine wave as your output. All right, and what else? Yeah, I guess that's it. So the only task that you need to do is come up with a square wave and then sine wave using integrator and differentiator. Right, so any question or clarification so far? None yet. Alright. So if ever that you guys have a question, so feel free to ask me anytime. So yeah, that's it for the integrator and differentiator. Okay, so if you guys do not have a question anymore, then you guys may now go. And a blessed afternoon to all of you. Goodbye. Goodbye. All right. Goodbye and thank you too.